Hi, finally, we reached part three, synchronization. There will be several recordings for part three. As I repeated many times in earlier recordings, synchronization is rather difficult for some of you. So I strongly encourage you to watch this video a few times. When you need it, either you send me email or even a Zoom call. I will be very happy to help you. This first lecture is rather short, probably an hour or so. It only introduced to you two important concepts, critical section and the mutual exclusion. They are the foundation of the next several lectures. And if you have watched the previous videos, you will notice that the words concurrent sharing appeared over and over. So if you do not remember the exact meaning of this concurrent sharing, I hope you go back and watch previous videos so that you can catch up quickly and properly. So the following topics about process synchronization will be covered throughout the remaining weeks of this semester. The first thing we want to talk about is why is synchronization needed? And we will introduce to you the concept of race conditions, critical sections, and so on in this lecture. Then we move on to the next two. Now, if we need synchronization, then what kind of solutions are available? If you don't get any help, or the system does not provide you with any help that can do synchronization, you could simply write the software solutions for you. These solutions do not need any help from the system. Or if you have chance to access the hardware, for an example, you could use interrupt or some synchronization-based instructions, such as compare and swap. We saw that when we discussed atomic instructions. Then there are some system supports. One of the most popular mechanisms is the semaphores. You may feel kind of difficult in using semaphore because this is your first experience in using a synchronization primitives. But don't worry, we will have a whole lot of examples. I will try to make the course pace slower. Then we will revisit race conditions. Why? Later on, you will know debugging a program with race condition is rather difficult. So debugging is an art rather than a science. There are so many tools out there that can help us to find race conditions in a program, but none of which is able to provide you exactly what the race condition is. Even though for a simple one, these tools may tell you a whole lot of places where race condition could be. So there will be so many extra places where you may find potential race condition rather than the real race condition. But as a programmer doing multi-thread programming for many years, I'll contribute some of my experience and share it with you. Then we move on to second important mechanism to do synchronization, the monitors. But in this lecture, we will first of all explain why is synchronization needed and the concept of race condition, critical sections from which the we learn mutual exclusion and other important concepts. In this lecture is all conceptual, nothing programming related nor proving related. So when we reach the next lecture, I'm sure you remember what I said previously. Find your discrete math book and refresh your knowledge in the technique of proof by contradiction. So let's take a look at a very simple example. In my experience, many of you simply missed the key point when you look at this example. This example looks pretty easy, but somehow some people just missed the most important key elements which will be discussed. So let's say we have a array A. Initially, it has 3, 4, and 5. This array is being shared by two processes, process 1 and the process 2. This integer array may be allocated in a shared memory. Now, process 1 update A1 by adding a 0 to it. Process 2 update A2 by adding the value of A1 to it. So after process 1 and process 2 finishes its execution, what is the contents of array A? We know A0 is never modified, so its value is definitely 3. But what are the other two? So think about it before you continue. Now, because each process has only one statement, and here we use higher level language statement interleaving. That is, process 1 completely finished its execution of this statement, and then process 2 starts to do it. Or process 2 starts to do it. When this statement is fully completed, then process 1 execute this statement. So we have two possibilities. That is, process 1 starts. Then after process 1 finishes, process 2 starts. So let's take a look what results you may get. If process 1 starts, it first and process 2 will start only if process 1 completes. So process 1 will see A0 being 3, A1 being 4. Therefore, 3 plus 4 is 7. 7 would be saved to A1. Therefore, after process 1 completes, the array in A would be 3, 7, and 5. 5 is not modified by process 1. So when process 2 starts, process 2 will see this result rather than the original 3, 4, 5. So process 2 take the value of A1 and the value of A2, add them together, we get 12, which is saved back to A2. So the result after process 2 ends. It is 3, 7, and 12. What if we switch the order, allowing process 2 to start first, followed by process 1? So in this case, process 2 starts and sees the array being 3, 4, and 5. Therefore, process 2 take A1 and A2 and add them together, which is 9. and use 9 to update A2. So after process 2 completes, array A contains 3, 4, and 9. Now process 1 starts. Process 1 sees the array being 3, 4, and 9. So process 1 take A0 and A1 and add them together and save that back to A1. The result would be 3, 7, 9. So depending on the order of execution of process 1 and process 2, you could either get 3, 7, 12 or 3, 7, 9. So depending on the order of execution, results could be non-deterministic. But in reality, the situation can be even worse. Why? Because here we assume that process 1 can complete the whole thing before process 2 starts, or process 2 can complete the whole thing before process 1 starts. Is this a reasonable assumption? No. Always remember, as a sequential programmer in your first years, you learn higher level language statement. You learn some assembly language statement in 23, 12, or 21, I assume. And you know, CPUs is not able to execute higher level language statements. CPU can only execute machine instructions. As a result, we need a compiler. Remember, we talk about compiling, linking at the beginning of the process concept. So the compiler would compile this statement to a set of machine instructions. And the compiler that compiles the source program of process 2 would also translate this statement to a set of machine instructions. So process 1 actually executes a set of instructions. So does process 2. So context switch could happen at any time, or interrupt can happen at any time between any two consecutive machine instructions. So that means interrupt could happen while we are adding these things, or it could happen while we are saving things. So the situation will become more complex. And that's the key. Always remember, CPUs execute machine instructions rather than higher level programming language statements. Therefore, we need a compiler to translate higher level language statement to machine instructions. When this set of machine instruction executes, interrupt or context switch could happen between any two consecutive instructions, and that makes the situation very complex. So let's explain this very complex situation by a very simple program. We have a global variable count initialized to 10. Process 1 adds 1 to it. Process 2 subtract 1 from it. So what would be the result after process 1 and process 2 completes? If your mindset is only set to higher level language statements, you will always tell me the result is going to be 10. Because you do this making count 11, then you subtract 1 from it, it's 10. Or you subtract 1 from it, it's 9, and then you add 1 to it, it's going to be 10, right? But why I have count, the value of count could be 9, 10, or 11. Well, the value of count being 10 is obvious, we just mentioned. But how come I could get 9 or 11? Reason is very simple. CPU does not execute this statement. Instead, it executes the corresponding machine instruction. So in order not to bother you to use a specific instruction set, I just use some hypothetical instruction because we don't need the real instruction set to explain the concept. Let's say the count plus plus is translated to 3 instructions. Load the value of count to a register and add the number 1 to this register, assuming we have only 1 register. Now, if adding 1 to the register, this register contains 11. And then save the value of the register back to count. So the value of count, if we look at process 1 only, it is 11. Now let's switch to process 2. So in process 2, it loads the value of count into a register, the only register. So the register value is 10. Now subtract the number 1 from this register. So in the register, the value is 9. And then we save the value of that register back to count. What is the result? In this case, 9. So when you do sequential programming, you don't care when an interrupt could occur. You don't care about when a context switch could occur because you have only one program flow, execution flow. But now we are doing process 1 and process 2 concurrently. And the meaning of concurrent is each process would have some progress at any time toward its end. So why we need this some progress is because we have a limited number of CPUs than the number of processes. Therefore, the system must make sure the CPU will be shared by many processes. So to ensure this can be done, we have to use interleaved execution. So when interleaved execution occurs, it's either due to an interrupt or a context switch for whatever reason. So interrupt could occur here between load and add, could occur between add and the store. By the same reason, interrupt could occur while process 2 is in execution here between load and subtraction, and between subtraction and the store. So the switching in or out by context switch between process 1 and process 2 could be very complex. Let's think about this. After process 1 loads the value into register, process 1 is switched out because of a interrupt. And then the system starts running process 2. Process 2 load the value here and subtract the value here, and then save the value here. Then process 2 ends. Then the system gives the CPU back to process 1. Process 1, it went to its counter and save the value of the result. This save the value back to this count overrides the previously saved the value in count, right? So as you can see, the problem is that execution flow may be switched in the middle of a higher level language statement. And the results could become even unpredictable. So when we talk about this concurrent execution, in particular interleaved execution, we cannot use higher level language statement. Instead, we must use instruction level execution interleaving, because interrupt could occur here, 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 or here, here. So we have no way to predict when an interrupt will occur. We have no way to predict when a context switch could occur. Therefore, it could be random. You run your program this time, a context switch may occur here, and next time it may be here. So the results could be even more unpredictable. So how do we say something about that? Let's take a look at example. we have to present the execution pattern in, in some way. And for beginners, the use of tables is very convenient. I will call this execution sequence. The execution sequence. Um, of course, when you are used to this kind of execution sequence, the table will not be that complex. So let's start with a complex one. It's not complex, just containing more information because we need it to explain the concept. So we use a table with a division line. On the left, it shows you the instruction execution of process one. And the right part shows you the execution of process two. Okay, so each row indicates the execution of an instruction. So process one start here, execute the load. And then switched out, the CPU is given to process two. And then process two executes load and subtraction. But an interrupt occurs causing a context switch. This time, the CPU is given back to process one. After process one does add and store, it's switched out. CPU is given back to process two for process two to execute its store. So we see the execution goes as follows. Process one does load, switched out. Process two does load, followed by subtraction and switched out. CPU is given back to process one. Process one does add, followed by store, and process one is switched out. Process two is switched in, it executes a store. Of course, you see so many different combinations. You have to find one that can illustrate the idea you want to present. So here is the instruction. The third column in each part is the value in memory. That is the value of count in memory. Now, in our presentation, we use register to do the calculation. Therefore, we did a only register in my hypothetical computer. So load count into the register, and then add one to the register, which changes the value of the register, but it does not change the value in memory, and then saves it. On the other hand, process two loads the memory value into a register. It's the only register. Subtract one from it, so the register is 9, but the count variable in memory is still 10. And then when process two continues, process two stores the value of 9 back to count. So in sequential programming, you'll only see the program in this way, in this way. You never care about there could be context switches. So here is the problem. Now, process one execute load. Loading the value of count from memory to register, and then process one switched out due to, say, an interrupt. Process two loads the value of count to register, which is 10, and subtract one from it. So the register of process two is 9, and then switch back to process one. Process one add 1 to the register, and then save the register value back to 11. After that, process two save this register 9 to memory. So this 9 overrides the previously saved 11. So in this sequence, in this execution sequence, the result is 9. Can you see that? But you want to say, wait a minute, you may have a problem. See, I subtract 1 from the register 9. How come I add 1 to the register? It should be 10 rather than 11, right? Good point. pause and think about it. I wait for you. Take as much time as you may need it, because that is very crucial. Okay, let's come back. Do you remember when we explained the concept of PCB and the discussion of context switch? In a PCB of a process, we have a set of register values. Remember that? So the register being used by a process is part of the context of that process. So when that process is switched out, the register value of the register used by that process will be saved to the PCB of that process. When the next process is switched in, the system would load the original value back to register. Do you remember that? I use apartment moving in and out as an example. So please review the context switch part and also the PCB part. So let me go through it again. When process one is switched out after executing load. So when process one is switched out, the value 10 in process one's register will be saved to the PCB of process one because it's part of the context of process one. So when process two starts running, the context of process two is loaded. So the value of the register, whatever it is, will be loaded back to register. So when process two loads the value of count into the register and subtract one from it, making it 9. Then process two switched out. So this 9, the value of 9, will be saved back to process two's context. So when process one gets back, after a context switching in. So what the value of the previous register? 10. So when process one gets its control back, before process one can continue, that context switch will load the original value of register 10 back to the register. So that when process one add 1 to its register, it's fine. 11 is process one's value. Process one will never get the value of 9 into here. As long as the system does not have a context switch bug. So always remember this. When you do a context switch, the register value will be saved. When you switch a process in, its original value of the registers will be loaded back. So this execution sequence shows you that the result is 9. Okay? So this 9 saved later than process one's store simply overwrites the 11 value saved earlier. So please pause. Make sure you understand this example, because we're going to use similar example over and over throughout this semester. So please pause before we go for the next one. Now, this one shows you a different context switch. As I mentioned to you so many times, you have no way to predict when an interrupt will occur. As a result, we don't know when a process will be switched in and when the other process will be switched out. So in this case, context switch allows process 1 to run. So load the value of counter into the register at 1 to it. After adding this value, a context switch occurs. So the value in the register 11 is saved to the context of process 1. And then process 2 starts its execution, and the old register value of process 2 is loaded back to the register. But anyway, process 2 would just load the value into the register subtract 1 from it, and then save its value back to 9. Now, process 2 is switched out, along with the value of 9 being saved to its context. Then process 1 is switched in. So the register value originally saved due to a context switch here will be loaded back to the register, which is 11. Then process 1 executes store, saving the value of 11 to verbal count. And this 11 overrides the previously saved value 9. So please pause, make sure you understand this example. It's so simple, we just switch the order of execution of these two save instruction. Then we'll have a dramatic change of the results. Okay? So you can see this type of unexpected results only if you use instruction level interleaving. You should not use higher level language statements. So these two examples are very important for us to define the concept of race conditions. In this course, we never define these technical definitions in a very formal or very theoretical way. Instead, we always choose to use an intuitive way so that this daily language is obvious enough, but at the same time, accurate enough. So a race condition occurs if these two conditions are satisfied. The first bullet says that two or more processes, look at here, I marked in blue. We must have two or more processes of thread manipulate a shared resource concurrently. In other words, this resource is being shared by two or more processes. These processes access the shared resource in an interleaved way or in a parallel way. They do it at the same time or do it in an interleaved way. You get some, just like the previous example, I loaded, and then you loaded, I added, you subtracted. We do it in an interleaved way. So we have seen three things here. We need to have two or more processes. They manipulate the shared resource concurrently. If these two or more processes do not have any resource, shared resource, then you don't have race conditions. Or if the two or more processes do not manipulate the shared resource in a concurrent way, you don't have race condition. So always remember three elements here. You need to have two or more processes manipulate a shared resource concurrently. So that means concurrent sharing. Then if you have this, the outcome of the execution depends on the order in which the access takes place. That is, the execution of the machine instruction. The order of this machine instruction being executed would affect the outcome. So we have seen an example. We will mention it again. So synchronization is needed to prevent race condition from happening. What does that mean? we only allow one process or thread to access that shared result, that shared resource without concurrency. So that is mutual exclusion to be discussed a few slides later. So synchronization is a very difficult topic for most of you, not all. In my previous 10 years, I have seen so many great students who can master this concept good enough for undergraduate students greatly. But for most of you, if your mindset uh, is fixed to sequential programming, you may feel difficult. So I would encourage you to start watching this video early. And if it is possible, watch it as many times as you want. Otherwise, you could miss a lot of things. So here, I'd like to talk about a few notes about regarding execution sequence. First of all, when you examine race conditions, you must always use instruction level interleaving to demonstrate the existence of a race condition. Never ever use higher level language statement because higher level language statements are not atomic. That's they are not executed without any interleaving. Higher level language statements are translated to machine instruction so that it can be executed by the CPU. Then interrupt or context switch could occur anywhere between two consecutive instructions. Secondly, instruction level interleaving can show clearly concurrent sharing. Here, the concept is not only sharing, but also concurrent sharing. Concurrent sharing means we access that variable in an interleaved way, or we access that variable at the same time. So finally, because we need to demonstrate the existence of a race condition, the consequence of a race condition is the results depends on the order of execution of those machine instructions. So how will you be able to demonstrate that the result will be different if you execute the instruction in a different way? The answer is so simple. You need at least two execution sequences, each of which leads to a different result. This is something you forget very frequently. Now, let me go through it. The last two is important. Use instruction level interleaving so that you can show concurrent sharing. You need to show two execution sequences that generates different results to justify that the order of execution can affect the results. Now, because of these two bullets, you should never use higher level language statement to demonstrate the existence of a race condition. We will explore this further by the next few slides. Now, throughout the years, many students just copy this example to say that we do have a race condition because the result is non-deterministic. Now, please stop here. Think about why without looking at the hint here. I would say this is a wrong example, even though I have two execution sequences. This is a wrong example to show there is a race condition. Please pause. Please do not look at this part. Okay, when you come back, if you try to recall the definition of the race condition definition, we need to have two or more processes. No problem. We have process one and the process two. And then we have a sharing. Process 1 and process 2 share this global array A3. And we provide two execution sequence showing the order affects the results, right? But what is missing is there is no concurrent sharing. Always remember the meaning of concurrent. Either we do it at the same time, or we do it in a machine instruction level interleaved way. So here, look at this. Process 1 finishes this, then process 2 does it. In this one, process 2 does it, followed by process 1. So there is no concurrent sharing. More precisely, both execution sequences fail to show that the array A is being manipulated in an interleaved way. Yes, array A is being shared, but it's not being manipulated in a concurrent way. Concurrent, you'd better to think is interleaved execution. Is there any interleaved execution of the instruction here and here? No. And this is why I recommend you remember, never ever use higher level language statement because it won't be able to show interleaved execution. Now, always remember this. Then we look at this machine instruction level. Now, process 1 loads counts into register, and process 2 loads count into register, subtract 1 from it, and add 1 to it. So from here to here. Process 1 execute its instruction in an interleaved way. That's concurrent way. And process 2 also executes its instructions in a concurrent way. So both process 1, process 2 share the variable in a concurrent way. Therefore, we have concurrent sharing, which does not occur in the previous example. So let me quickly go through it. Hope you don't mind. Process 1, load the value and switch out and or in with machine instruction level interleaving. Process 2 does it. So from here to here. Process 1, process 2 manipulates the value count in an interleaved way. So we demonstrated concurrent sharing. Now, let's fit what we have learned so far to the race condition definition. One, we have two processes. They share a global variable count in a concurrent way. Do you see that? And the results are different. If you allow process 1 to save first, followed by process 2, then the result is 9. Now, if you switch this save, then the result will be 11. Therefore, with two processes that access the shared resource in a concurrent way, the results are different if the order of execution changes. So this example completely fits into the definition of race condition. I hope you remember this and understand this. Now, I assume you remember this, okay? And if you suddenly find out you forgot something, you just rewind a little bit. Now we know race condition is a troublemaker. Actually, you have no way to find race condition. I should say you have no efficient way to find race condition with a debugger. Because once you use a debugger, you change the behavior of the execution of the program. Then the existing race condition may never happen. So we need to find some way to address this issue. The concept here is referred to as critical section. What is a critical section? It is a section of code in which a process accesses shared resources. So let's return to the counter variable, count here, being shared by process 1, process 2, process 3. So a critical section with respect to variable count is the code with which you access the variable count. So process 1 has count plus plus. So this statement accesses this count variable. Process 2 use it, and process 3 also use it. You may want to say, hey, the count is just we just print it out. Oops, it's C out. I use C++. Anyway, you just think about this, just a print. So in process 1, process 2, process 3, at least we have found 3 statements with which we access the variable count. Or there could be other places where variable count is accessed. So you just circle them out, single them out with a frame or use a mark pen. So these are the critical section with respect to the variable count. Because with this statement, you access the variable count. Now, if you have another shared variable, say sum, and all 3 processes may also access this global variable sum, then use a different color marker to mark it. So once you do that, you have circled out or singled out all critical sections with respect to the global shared variable sum. So this is very easy to do. If you read your program carefully, I'm sure 100% you could find all critical sections with respect to a global variable. Then here is the key concept, mutual exclusion. To avoid these race conditions, the execution of this critical section must be mutually exclusive. Remember, one process want to count the other process, subtract 1 from count, the third process simply print out the value of count. What if all 3 processes access that 3 critical section in an interleaved way? Well, results could be different and unpredictable. However, if, let's say, just focus on the variable count, if we only allow one and only one process to be in its critical section, executing that statement, only one, no other process could execute their own critical section with respect to count, we are very safe. Because while I am modifying the value of count, I know no one would be able to access variable count in the concurrent sharing way, right? Because there's no concurrent share. I am there doing my stuff, and everybody must stop doing that. And this concept is referred to mutual exclusion. That is, we circle all critical sections with respect to a variable. Then I have to make sure, as long as I want to access a critical section, I am the only one. Rephrase this in a different way. All of the critical sections with respect to variable count must be mutually exclusive. Or At any moment, there is no more than one process that could execute the critical section with respect to verbal count. So I have provided you with three different ways to say things. You could use whatever way as long as it's clear. So a the critical section problem is to design a protocol that will add some statements. With this statement, mutual exclusion can be guaranteed. So we add something before and after the critical section so that mutual exclusion is guaranteed. So how do we do that? That's difficult. So please follow me carefully. If you listen carefully, you will find out my pace is slower. I will be even slower in the next lecture. So suppose this is a critical section with respect to a global variable. We need to add some codes before the critical section and some codes after the critical section. We need to add two parts. The part before the critical section is referred to the entry section or enter section. The one after the critical section is referred to as the exit section. So what these two sections are doing, we will talk about it later on. So assuming that you know how to add a few statements before the critical section for the entry section, then you know how to add some statement to the exit section, so on and so forth. So suppose we have a solution for that. Next lecture, we will talk about several solutions. Don't worry about that. But I hope you watch the video very carefully and ask questions. So that is the critical section problem. A good solution to the critical section problem must satisfy the following three conditions: mutual exclusion, progress, and bounded waiting. In the past, I found out most students understand the mutual exclusion easily, and a large portion of students understand the bounded waiting condition to a large degree. But many of you usually could not understand the progress condition in a proper way. So when we talk about the progress condition, please pay more attention to my lecture. So the solution that's adding statement to the entry code and adding statement to the exit code, the solution cannot depend on the CPU speed, cannot depend on timing, scheduling, policy, and all other external factors. That is, you cannot assume anything outside of your program. In other words, the correctness of a solution must be intrinsic to your program without any assumption about external factors. Remember this. So the meaning of mutual exclusion, as we explained earlier, if a process P is executing in its critical section with respect to a global variable, no other processes can be executing in their corresponding critical section. That's only one can be in the critical section with respect to the same global variable. So the meaning of the global, the entry protocol goes as follows. Currently, you just think the entry protocol can do this in a magical way. So the entry protocol should guarantee that if someone is already in a critical section, the entry protocol will block the next one who wants to enter. In other words, if someone is already in a critical section, the entry protocol must block everyone who tries to enter. This is easier said than done. You will scratch your head in the next lecture. So when a process finishes its execution in its critical section and exit, the exit protocol must know this and inform the entry protocol so that the entry protocol will be able to know the one who was there has gone. That critical section becomes empty. And then the entry protocol allows the next process to get in. That's a key question. If we have so many processes blocked due to the fact that when those processes came, someone was there and blocked by the entry protocol. So when the critical section becomes empty, they usually notified by the exit protocol that the entry protocol must find a blocked process to continue so that it could enter the critical section. And that one is the only one. So this is the meaning of mutual exclusion. We will talk about it in the next lecture. Now, progress condition. This is something many people confused and couldn't remember. So the progress condition has an assumption. This means suppose there's no processes in the critical section. In other words, the critical section currently is empty. No one is there. And there are some processes waiting to enter. When could this happen? The process was there exited. Then the critical section become empty. As we mentioned earlier, when we talk about mutual exclusion, the exit protocol must be able to inform the entry protocol saying that the guy who was there exited. So you could send the next one in, okay? So for the entry protocol, when it sees that, okay, the critical section currently is empty, and we have some processes waiting to enter, then two conditions must be satisfied. The first condition says only those processes that are waiting to enter can participate in the competition to enter the critical section, and no other processes can influence this decision. In other words, suppose by the time the critical section is empty, and the processes A, B, and C are waiting to enter, but they were blocked because someone was there. And the process D is elsewhere. So that means the entry section must implement it in this way. The entry section must select a candidate from process A, process B, and process C, and only one candidate can be chosen so that that candidate could enter the critical section. In other words, at this moment, process A, process B, and the process C compete to enter. But the entry section can only pick one. And process D, which is elsewhere, not interested to enter. Process D cannot have any influence to this candidate selection process. I usually use this example. Suppose at home, or you rent an apartment and 4 people are living there. but there is only one bathroom. What would you do? You would not allow someone to share the bathroom with you concurrently. That's for sure. So that bathroom has to be used in a mutually exclusive way, right? So for some reason, you have four persons living in that apartment, A, B, C, D. You are A. So nature is calling. You want to get into the bathroom. But B encounter the same situation. A and B, you and B, run there. But C was there and just exit. So D is elsewhere studying. So the entry protocol for that mutual exclusively used bathroom will determine either you, A, or B would get the bathroom. The entry section must choose from you or B. They don't care the one just left, C, or the one who has no intention to do whatsoever in the bathroom, because D is studying. So this is something we talk about here. In a very plain language, is when we have to choose a candidate to enter the critical section, when the critical section currently is empty. The entry protocol must select a candidate from those who are waiting to enter. Those who are not waiting to enter have no say about it. Those who are not waiting to enter, usually I will call outsiders. Okay? But there could be a situation like this. What if C is there in the bathroom? You A and B wants to use the bathroom. So you wait outside because the entry protocol C knows C is there. Due to the bathroom must be used in a mutually exclusive way, the entry protocol blocks you. Probably you would just say the entry protocol is the guard of your bathroom. So when C gets out, then the entry protocol or the bathroom guard will pick one from you and B. Okay, that's what I said. But what if D is a very selfish guy? Okay, so D, for some reason, upon exit of the bathroom, D locks the door up with a lock. So when you and B or even C wants to enter, as you know, the entry protocol can only select a candidate from you, A, B, or C. But this time, the entry protocol cannot do anything, allowing one to enter because the door is locked by someone who is irrelevant, an outsider. So in this case, an outsider has influence to the selection of a candidate because the entry protocol cannot select anyone. So this is condition one, the outsider influence. The next one goes as follows. The entry protocol must select a candidate in finite time. In other words, the selection of a candidate cannot be postponed indefinitely. The decision making for selecting a candidate is finite. So the meaning of finite is very interesting. What is finite? 1 second is finite. 1 minute is finite. 1 hour is finite. 100 days is finite. 1,000 days is finite. 1 million days is finite. 1 trillion days is finite. So as long as you can write a number completely, that number is a finite number. So what is not finite? That is, you are blocked there. The decision has never been made. It cannot be made in your lifetime, finite time. So the second one is when the entry protocol must select a candidate. This selection, this decision-making time has to be finite. Therefore, one of the waiting processes can be selected to enter the critical section in finite time. So let me quickly go through these two. The first one is when the critical section is empty, the entry protocol must select a candidate from those waiting ones. An outsider that's not a waiting one cannot have any influence upon this decision. And then the decision-making time for selecting a process must be finite. So stop this video before continue until you understand completely what progress means. Now, if you moved here, I assume that you know completely. The third condition is bounded waiting. This one looks like the progress condition, but actually it's completely different one. So some of you may mix them up, thinking they are the same, just saying it in a different way, wrong. So it means after a process made a request to enter its critical section, and before it is granted a permission to enter. So I come to enter, and then the time I am able to enter, there exists a bound on the number of turns that other processes are allowed to enter. For example, suppose you want to access the bathroom and you are blocked by the entry protocol. Then B comes in waiting, and C comes in waiting, D comes in waiting, and so many people are coming waiting. So once the bathroom becomes empty, one of you is allowed to enter. But what if it's not always you? That's a big problem. You are waiting there probably forever. So bounded waiting means from the time I make a request to enter to the time I actually enters, there are only a number of processes could be ahead of me. And this number is bounded. I will explain the meaning of bounded later. So suppose this bound is 3. You want to enter, but when the critical section is empty, you are not selected. Someone entered before you. In this case, you wait for 1 round. And then the next time the critical section becomes empty again, unfortunately, you are not picked. Someone enters before you, so you wait for 2 rounds. Suppose the bound is 3, then the third one who enters. So the 4th time is yours. So if the bound is 5, there are only 5 people could enter the bathroom before you enter. So you are the 6th one. So return to some details. This bound is definitely has some relationship with respect to the number of processes that want to enter, right? You cannot have 1 million processes wanting to enter, but the bound is 2. That is ridiculous. Just like you learned in data structure. If you have n data items to be sorted, the complexity of an algorithm is order something. Say, insertion sort is order n squared, heap sort, merge sorted, or order n log n, and so on. So this bound, this value has to be bounded, just like a n log n is the upper bound of the number of comparisons that has to be performed. So if you have n processes running in the system, so this bound is very likely a function of n. Say log n, n log n, n square, or n square root of something. So who is going to find this bound? The one who designed the protocol. Okay. Suppose you have n processes that involved in this concurrent system, and the bound is log n. Then, if you want to enter and the bound is log n, then you wait for log n turns. That is, you wait for log n processes, whether they are the same or different, doesn't matter. There are at most log n processes that could be ahead of you. Then log n plus 1 would be you. So this is the meaning of bound. Okay, so this is the meaning of bounded waiting is given a system of some number of processes and you design a protocol. From your protocol, you have to derive a bound, just like you derive n squared n log n for a sorting algorithm, or log n for a binary search algorithm, something like that. You find the bound with respect to the number of involved processes. Then you prove that is the bound does work. That is, for every process, when it wants to enter the critical section, no more than that bound runs will be ahead of you. So if that bound is k, then at most k plus 1 is you. You may enter in waiting for less than k runs. Okay, not always the full value. It could be the first one is you, or the second one is you, rather than k plus 1. Okay, so then some of you may not be math oriented, so I need to explain the difference between finite and bounded. They are two different things. Finite means let's just use writing an integer down. As long as you could write a sequence of digits you'll stop, that number is finite. So finite decision making is you could write down how many times it spent. As long as you could write down the number and stop, and that is finite. And what is infinite, you cannot stop because just keep going like a 3.151415, it never ends, right? Square root, it never ends. But square root of 4, it's just 2. I hope you understand the meaning of finite and infinite. And the bounded means the number you jot down has an upper limit. So if the bound is 10, then whatever you can write is 1, 2, 3, 4, 5, 2, 9, and 10, right? So if you have a bound, that bound has to be finite, because you can write down the number of runs for those processes to enter ahead of you. So it's definitely a finite number. So let me put it this way. Bounded is always finite, but finite may not be bounded. Say the bound is 10, and 11, 12, 13, 14, 100, these are all finite numbers, okay? So please understand the difference between finite and bounded. So let's talk a few more details between progress and bounded waiting. Look here. Some of you implicitly think this statement being true. Now, let me warn you, progress does not imply bounded waiting. Progress only says a process can enter within a finite decision time. This is the decision time. That is, the enter protocol will spend finite time to select a candidate. It does not mean which process can enter. And there's no guarantee for bounded waiting. For an example, suppose three process A, B, and C try to enter, and the current critical section is empty. Then the entry section will pick one of you, say in two minutes. Let's say A. Then A enter and exit. A may come back, want to try again. So right after the critical section becomes empty, A comes back. So we still have three processes to wait. And if A is lucky, A could be picked again. Or if A, B, C are waiting, A enters. A is select in finite time. And then upon exit, we have B and C there, right? So the entry protocol is going to select either B or C in finite time. This time, the entry protocol, say in 1 second, it picks B. So C is outside, B is inside, A is somewhere. So while B is inside the critical section, A comes back. So when B exit, A and C are outside. But it's very likely the entry protocol pick A again. So this pattern could repeat over and over, and C has no chance to enter. But in this case, because the entry section, every time it picks a process in one, but the entry code never picks C. Therefore, for C, it may never have a chance to enter. So in this case, the algorithm satisfies progress, but it does not satisfy bounded waiting because C can wait there forever or for a very, very long time, larger than any bound you can write it down. Okay, so understand this. Then bounded waiting does not imply progress either. Bounded waiting only guarantee a waiting process will be able to enter after a few runs. That a few runs is bounded. It never guarantees that this process can enter. Okay, who can enter is determined by the candidate selection in the progress condition stated. So even though we have a bound, all processes may be locked up in the enter section. That's due to infinite decision time. Did you get it? Say, suppose three processes are involved. The bound is 3. But the entry protocol is so badly written, it may take infinite time to make a decision. Therefore, no one can enter. So if bounded waiting is true, it does not mean progress is true. So progress and bounded waiting are independent of each other. None of them can imply the others. Therefore, we have 3 independent conditions for designing a good solution to the critical section problem: mutual exclusion, progress, and the bounded waiting. As I mentioned to you earlier, most students may be confused by the progress condition. And some of you may be confused by the meaning of bound. And some may even think progress and bounded waiting are the same thing. On this slide, I explain to you that they are two different things. None of them could imply the other. Now we have a few other terms you may see in other literatures. The first one is deadlock freedom, or sometimes we would just say deadlock free. Its meaning is if two or more processes are trying to enter the critical section, one of them will eventually enter. So that means the entry section will not cause any deadlock. Let me repeat this. If two or more processes are trying to get into the critical section, one of them will eventually enter. We don't know which one. Just as long as there's one, it's okay. So this is the progress condition without the outsider influence, right? The progress condition says that when the critical section is empty and some processes are waiting, we can select one, allowing that one to enter in finite time. But in deadlock freedom, it says, as long as the critical section, whether it's empty or not, as long as there are processes waiting, eventually one could enter. It did not say finite time, but as long as one can enter, it means the decision time is certainly finite, right? Therefore, the deadlock freedom concept is part of the progress condition, the finite decision part. The next one is starvation freedom or starvation free. It says if a process is trying to enter its critical section, it will eventually enter. What condition this starvation freedom is related? Well, definitely a deadlock, right? Sorry, the bounded waiting. This means as long as a process is trying to enter, it will eventually enter. It does not say how long does this process will wait. Unlike the bounded waiting, we have a finite bound. We have a bound for it. So think about these several questions. Does starvation-free imply deadlock-free? Okay. Does starvation-free imply bounded waiting? We just answered it. The answer is no. The third one, does bounded waiting imply starvation-free? Think about this. I'm not going to tell you the simple answer. Now, the fourth question, does bounded waiting and the deadlock-free imply starvation-free? That is, if we have bounded waiting and the deadlock-free, then do we have starvation-free? Okay, think about this. Now, these are the questions here. Hopefully, you'll read the answer. So this is the end of our first touch about synchronization. It appears it's longer than I expect. That's because we inject so many examples and talk about example in real life and repeat several things. In the future videos regarding related to synchronization, you'll feel that my pace could even be slower. So please review this set of a video, in particular this one, carefully. If it's necessary, watch it several times. The key word I did not explain carefully, the concurrent sharing, was explained earlier. And we use the concept with machine instruction interleaving to define race condition. So let me stop here. See you next time. Goodbye.